Okay, today's lesson is about compound events and dependency. So we're actually just look at an example. We're going to do a question about the Denver Broncos, but this is an interesting situation because their probability of winning would probably be different at home and away. You can say that there's always like a factor that would allow a team to be better at home versus away, but just this is like a scientific one where the players are actually more used to the thinner air. So this is a warm-up question. So when you toss a coin, N of S is 2 because there's two outcomes, heads or tails. But if you toss 3 coins or 4 coins or 5 coins, how many ways, or even 2 coins, how many ways would there be? And so I invite you to think about that, and we'll talk about it in a second. The learning quote today is compound events and dependency to calculate theoretical probability. So we're going to learn what compound events are and what it means to be dependent. And so the success criteria, so how you know you'll be successful is if you can display independent and dependent events using a tree diagram, can calculate simple probabilities with 2 independent events, or calculate simple probabilities with 2 dependent events. So here's back to the coin toss. So this is what a tree diagram would look like. And so this is a simple one for tossing 3 coins. And you're going to do one toss at a time, and then the second toss will go off the first toss, and so you have heads and tails each choice. What's helpful to do is to trace out the outcomes and say this branch here would call us head, head, head. That would be one way to do it. Head, head, tails another way, and so you can actually clearly see that there's 8 outcomes. Probability of 2 or more heads. Then now that have all the outcomes, you can use the tree diagram to count the number of times you get 2 or more heads, and you can see these 3 here are the cases where you have 2 or more heads, and there's also this one as well, and I think that's it. So it's 4 out of 8 or 1 out of 2. Compound event are events that are created by combining two or more events, and so we've seen earlier in the last lesson about how we can have 2 different events and like 2 different Venn diagrams, but we're only doing one thing. With compound events, we're actually like taking 2 things, and so we're actually going to see like A and B being 2 different actions that we're going to take. So the chance of hitting a target is a compound event because it depends on the wind, and it also depends on how good you are. The outcomes in a 4-coin flip are compound events because you're combining all the outcomes on every individual coin. So it doesn't have to be 2. It could be more than that. And then we've already seen finding the sum of 2 dice is a compound event because it's combining the sums of the 2 dice. An example here, so traveling from Helsinki to Poland. And so first of all, he's going to go from Toronto to Warsaw, and then Warsaw to Helsinki. So how many different ways can he travel? So here's the tree diagram. So Toronto to Warsaw is 4 different ways, and then Warsaw to Helsinki is 3. And so you can clearly see all of the different outcomes. And so you can see the 12 ways that he can travel. Is there a quicker way? And so this is what we're actually going to call the slot method, or the fundamental counting principle. You just multiply 4 by 3. The probability takes H2. You can see all the flights with H2 in them. So it looks like there's 4 ways, and so 4 out of 12 or 1 out of 3. That's the fundamental counting principle. So if one action can be performed m ways, the second n, and the third p, the total number of choices is m times n times p. In this activity, we're only doing the 2 choices, so 2 things multiplied by each other, but you can keep going as well. So we actually use this word and so we notice that like he's taking a flight to Warsaw and a flight to Helsinki, and so we're combining those 2 outcomes, and so by saying and, that's actually what tells you to multiply. And so like the word and can actually be replaced with the symbol multiplication. So 2 flights, and the slot method is basically you put down 2 slots if you've got 2 flights to take, and then you can say what's the number of ways to take the first flight, the number of ways to take the second flight, and so you get those 12 total ways. And so that's actually what we call the slot method, where you put down slots and you ask yourself, how many ways to get to Warsaw, and then how many ways to get to Helsinki from there. The probability, if you want to know the probability right away, you can actually um, you can combine the fundamental counting principle and just say n of s is 12, n of a we know, so we want to take the first flight to Warsaw, so there's only one, and the one of the last two flights to Helsinki, so there's two, and so n of a would be 1 times 2, which is 2. The probability of this, so the answer would be n of a over n of s, and so it's 2 over 12. Notice we're still calling it P of a, so we're still saying it's the event that we want, and that's to take the first flight to Warsaw and one of the last two flights to Helsinki, so that's the probability of A. What we're going to do in a minute is we're actually going to introduce another one, and so we'll do the same question, but we're going to have A and B in there. So the fundamental counting principle, so that idea of multiplying for probability is just extended, so that, and if we said the first part of the compound event's A and the second is B, we could say that the probability of A and B, so the intersection of A and B, like doing both of them, is the probability of A times the probability of B. So back to Mr. Jordan, we can say if the probability of A is 1/4, 1/4 of the time we're going to take the first flight to Warsaw, and the probability of B is 2/3, we can actually do that probability by saying, by using this formula, calling A being the flight to Warsaw, and B is the event of taking one of the last two flights to Helsinki, and so we can say it's it's kind of like the slot method again, but you're actually putting fractions in those slots, 1/4 times 2/3. And it gets you the exact same thing. So it's just like kind of doing probability all at once rather than doing n of a and n of s at the same time. This same formula does work for n as well. So n of a and b equals n of a times n of b, and that's how we did it just a second ago. But we called a total like the whole event. So it's just another strategy. Independent trials. So trial is independent if it acts independently of the previous trial. Rolling dice, flipping coins are all independent trials. It's dependent if the number of outcomes depends on what happened before. So drawing cards without replacement, so not putting the card back after you draw it. Chance of rain and success in a game. And so we'll see an example like that. So are you better when it's raining out? Does that change your chances? Tree diagrams are very helpful for dependent trials because they allow you to see there's only a certain number of ways. The conditional probability formula is for dependent events. It's the exact same formula, except for this little second part, it's what we call probability B given A. So that's the probability of B given A. And so it's that given A has already happened. For dependent events, this often requires taking one away from n of s, but so it can depend on the situation. It really can depend on the situation. So you really have to think about what you're doing there. So a couple, like very similar example. So an independent event would be like, what's the probability of choosing a 3 and then an ace? And so we could say it's the probability of A times the probability of B. A dependent event would be like, what's the probability of drawing 2 kings in a row if you're not replacing them? So this one, you're replacing it. And so for the first one, you actually get 4 to 52 because that's like drawing a 3 is 4 to 52. And then 4 to 52 again because drawing an ace is 4 to 52. And it's out of 52 because you're replacing the card. And so notice how these are really just the probabilities of each of these happening. Probability of a 3 and probability of an ace. And the second one is the king, 2 kings in a row. So probability of a king we know is 4 to 52. But the probability of king, given a king has already come out, is 3 out of 51. If this was a king then an ace, it would be 4 to 51. But it certainly matters that n of s is kind of changed for that second part. Here's a new example. So if the Denver Broncos have an 80% chance of winning at home, 60% chance of winning on the road. These aren't real stats, it's just hypothetical. What's the probability that they win any random game in the season? And we're going to say that they have 10 games left in the schedule, and it's a 70% chance of being a home game. So the question actually has two cases, and so often we're actually going to, when we see multiple ways to do this, so you can either win at home or win on the road, we're actually going to use the word or. And or is actually just means that we're going to have to add them up after. And so the first case, winning at home, A is the event of a home game, B is the event of a win, given it's at home, and we know that we have a 70% chance of it being a home game and 80% chance of it being of winning at home. We can do 0.7 times 0.8, which is 56% chance of winning at home. The second case is winning on a road, and so we know that the probability of it being a road game is 30%, because we're just going to say that there's 3 games that could be a road game. And the probability of winning, given it's a road game, is only 60%. And so if we multiply 0.5 times 0.6, the probability of winning on the road is 18%. The probability of it being a road game and them winning is 18%. If we add those two up, we actually have a 74% chance of winning any game left in the season. So we just say there's 10 games left, and you have a 74% chance of winning any of those, really the next game. Similar to that question is this ODSS question here, and you can try that by separating the different cases. You can also draw a tree diagram for rain and winning. And then there's some questions to practice.